Hello, I want to talk about our even and odd functions because we've been spending a lot of time talking about even and odd degrees of a function. So there's a big difference between the two things that I just said. Even and odd functions are called even and odd because they display even and odd symmetry. So to be an even function, you must have even symmetry, and the same for odds. So let's review what we've already known about even symmetry when we were looking at those power functions, and we had pictures that looked like this, and you might recognize that as x squared, but we said it had even symmetry because when I rotate it around that y-axis 180 degrees only, right? It's just that reflection across the y-axis. When I do that, I get a new picture that looks identical to the old one, right? So I did that reflection across the y, and I got the same thing. So that is symmetric across the y. And we call that even symmetry. So, and it just so happened in the power functions that this was an even degree as well, okay? But not in all polynomials of an even degree will have even symmetry. For example, what if I had a picture that is clearly an even degree polynomial? This function has an even degree because both ends are up, but he does not display even symmetry because if I rotated that, I would get a new picture on the other side that looks like this, very different than my original function because he's on the left side instead of being on the right side. So he does not have his even symmetry, therefore he is not an even function. So separate these two ideas of being an even function from having an even degree, okay? And then we can do the same argument with the odd. And as we look at this odd symmetry, we had looked at the power functions. Remember those very special case polynomials where they all came out basically looking like the snake or the disco. And we said, wow, these are symmetric across the origin. And the best way to think about it is you do one reflection across the y-axis and then a second reflection across the x. So we did that one reflection, then we're going to do this one, and that ends up with that being up instead of down, and guess what? We are right back exactly where we started. So after this sort of across the y and then across the x, which is the same as what we call a symmetric across origin, getting the same picture. So it is symmetric across the origin. This has odd symmetry. Now, when we looked at our polynomials, we said they were even, or an odd degree based on that highest exponent. But symmetry isn't even or odd, it's even, odd, or neither. Most of the time, our functions are going to be neither odd nor even symmetry. So just to give you an example of something that's not so special, right? Let's do this. Maybe I have the disco shape, that odd degree, but because he's not symmetric across the origin, and certainly not across y either, he is a neither symmetry. So that would be an example of neither symmetry. Let's go back for a moment and look at our even symmetry and see what's really happening. Let's find a way that we can define this algebraically rather than just as a reflection, which it is. That's more of a description. I want something more now to be a definition. So as I look at this, what I want to notice is that if I pick a value of